Now we will continue solving more examples on kinematics for motion in 2 dimensions, and especially we will take a look at projectile motion. Okay, so the fourth example is a particle starts from the origin with velocity 5 I hat meters per second at t is equal to 0 and moves in the xy plane with a varying acceleration given by 6 square root t j hat, so it's in y direction, where a is in meters per second squared and t is in seconds. Determine the velocity of the particle as a function of time. Determine the position of the particle as a function of time. So I first of all note that the initial velocity at t is equal to 0 is 5 I hat meters per second. So this is telling me that the x component of the initial velocity is 5 meters per second. Y component of the initial velocity is 0 meters per second. On the other hand, I have acceleration, which is 6 square root t j hat, which tells me an x component of 0 and y component of 6 square root t meters per second square. So let's start with finding the velocity as a function of time. I see that the acceleration ax is a constant, so the x component of the velocity is a constant. It's a constant of the motion, and that's because dvx dt, which is ax, is 0. It doesn't vary with time. On the other hand, if I look at dvy dt, which is the y component of acceleration, that tells me a change in the velocity delta vy, integral from 0 to t, 6 square root t dt, which is ay dt. So that is going to give me a delta vy, which is vy at time t minus vy at time t equals to 0, the initial y component. Because at t is equal to 0, I have 0 y component. I can conclude that this is vy of t, and that is 6 divided by 1 over 2 plus 1, t to the 1 over 2 plus 1, which is 3 over 2. So this is 6 times 2 over 3, t to the 3 over 2. So this 3 will make this 6, 2. So I will have 4 t to the 3/2 meters per second. So I know x component is a function of time and y component is a function of time. Therefore, I can report velocity as a function of time to be 5 I hat, the constant x component, and time varying y component for t to the 3 over 2 j hat in meters per second. So that's the answer to part A of the problem. Now we want to determine the position as a function of time. So in part B, what is the initial position? It starts from the origin. Okay, so initial position, r initial, or r at t equals 0, is 0 I hat plus 0 j hat in meters. Now the velocity of the particle is the derivative of position vector dr with respect to time, dr dt. So we see that the displacement delta r is the integral from 0 to t v dt, and delta r is r at time t minus r initial. This is the integral from 0 to t 5 I hat plus 4 t to the power 3 over 2 j hat dt. So I can find r as a function of time to be 5t I hat plus, now taking the integral of t to the 3 halves, 4 divided by 3 over 2 plus 1, t to the 5 over 2 j hat. So this will be 5t I hat plus 4 times 2 over 5 t to the power 5 over 2 j hat, and I have the final answer here. Our position as a function of time is 5t I hat and 8 over 5 t to the power 5 over 2 j hat measured in meters. Okay, so in this example, we have a particle starting its motion from origin. It has a constant x component of velocity because it has an acceleration, a time varying acceleration on the y-axis 6 square root t j hat. So we determine the velocity as a function of time by looking at the acceleration velocity relationship dvy dt is ay, and that gives us the time varying y component, and constant x component was 5, so it is 5I hat plus 4t to the 3 halves j hat. Then we look at the position vector velocity relationship. Instantaneous velocity is dr dt, therefore the displacement is the integral from 0 to t v dt. We take this integral and find both x and y components of the position vector directly. So it is 5t I hat plus 8 over 5 t to the power 5 over 2 j hat, which is measured in meters. Okay, let's move on to projectile motion. In a popular lecture demonstration, a projectile is fired at a target in such a way that the projectile leaves the gun at the same time the target is dropped from rest. Show that if the gun is initially aimed at the stationary target, the projectile hits the falling target. So this is the story. We are going to release at the target from rest, and at the same time we have a projectile this gun shoots, which is basically aimed at the target, and the problem is to show that it will hit the target as it falls down. So we have to analyze this problem from two different motions, because we have the motion of the target and we have the motion of the projectile. So we have to analyze both of them at the same time and determine if when I reach the time of flight they're going to coincide on the y-axis. So that is the idea. So let's start with analyzing the motion of the target. So the target has no initial velocity. So initial velocity y component of the target is 0 because it is released from rest, but it has a y component of acceleration, which is the gravitational acceleration minus g meters per second square. So we are in a gravitational field. Gravitational acceleration g is pointing down. If I were to plot the velocity y component as a function of time, I would see that because I have a constant acceleration motion, vt graph would be linear, and when I reach the time of flight at time t is equal to t0, which I call time of flight, this is going to reach a final velocity Vy prime of the target. Okay, so the difference Vy prime of the target minus initial velocity of the target is the integral from 0 to time t0 ay dt, which is minus g times t0. So it's going to reach a velocity minus g times t0 at the end of the flight. Now, if I look at the displacement on the y-axis is delta y of the target. It is the integral from 0 to t0 Vy dt, Vy of the target dt. And how does the velocity of the target vary with time? Constant acceleration motion minus gt dt, and I find that this is going to be minus 1 over 2 g t0 square. So I find that the initial position of the target and final position of the target are related by the target position at the end of the time of flight minus the initial position of the target is minus 1 over 2 g t0 square. So t0 is the time of flight or time of collision. I'm suggesting that there will be a collision. And I also call the distance the projectile travels on the x-axis the range. xt is the range of the projectile motion. Okay, so I find that at the time of collision, the target is at a position, initial position of the target minus g t0 square over 2, which is what I call yt in this figure. So this is basically yt. Now, if you look at this angle, theta initial, with the angle with which we're shooting this gun, you can see that the tangent of this angle is related to the initial position of the target and the range of the projectile. So we can see that also we note that tangent of this angle, because it's pointing exactly at the initial position of the target, is the initial position of the target divided by the range of the projectile. So the initial position of the target is actually the range of the projectile times tangent theta initial. So we can write this final position of the target to be the range of the projectile tangent theta initial minus 1 over 2 g t0 square. So basically, when I analyze the motion of the projectile motion, I'm going to check this value for the final y position of the projectile and see if it matches the final position of the target. If they do, then they will be having a collision. So let me analyze the motion of the projectile. So for this one, I have the x component. As you can see, there is an initial velocity of the projectile. It is fired with an initial velocity. So I have the initial velocity of the projectile has an x component, vi x of the projectile is the initial velocity of the projectile times cosine theta initial. And there is no acceleration on the x-axis. So I find that the range xt minus 0, so assuming that my x and y axis have this origin at t is equal to 0, so xt minus 0, the displacement on the x-axis, is the integral from 0 to t0, the x component of the velocity dt. This is a constant because ax is equal to 0, so this is going to be equal to the initial velocity cosine theta initial times t0. So this means there is no time dependence on the x component. Therefore, I can see that this t0, the time of collision, can be written as xt divided by the initial velocity cosine theta initial. So let's keep this in mind from our analysis of the x component of projectile motion. Now let me concentrate on the y component here. So I'm done with the x component. Now for the y component, I have an initial y component of the velocity, which is the initial velocity magnitude multiplied with sine theta initial. So on this axis, I also have an acceleration which is minus g meters per second square. So if I look at the change in the velocity on the y-axis, it is final velocity y component minus final velocity, initial velocity y component, is integral from 0 to t0 ay dt, which is minus g t0. So I find that the final velocity of the projectile y component will be initial velocity vip sine theta initial minus g t0. Let's do this again. Okay. Now, how about the displacement on the y-axis, delta y, which is the yp at t0 minus 0, because initially it is at the origin. So this is the integral from 0 to t0 vy projectile dt. Now I can work on this yp at t0 is the integral. So the integral will give me 0 to t0 vip sine theta initial minus gt0 minus gt actually at time t dt. So this will give me for the final position of the projectile to be vip sine theta initial t, which becomes t0 minus 1 over 2 g t0 square. And for t0, I can substitute xt over vip cosine theta I, So I can take this here, yp at t equals t0 is VIP sine theta I times t0. For t0, I substitute the range xt divided by VIP cosine theta I minus gt0 square over 2. You can see that the initial velocity, initial speeds will cancel, and my final answer will be for this, the final position of the projectile at time t equals t0 is xt sine divided by cosine is tangent theta I minus 1 over 2 g t0 square. So this is my final answer for the position of the projectile at time t equals t0. I compared it with the final position of the target, which is xt tangent theta initial minus 1 over 2 gt0 square. It's the same answer here. So what is the conclusion? So notice that the final position of the projectile at the time of collision is equal to yt, which is the final position of the target. So indeed, the projectile hits the falling target. Therefore, the statement that was suggested by the problem is correct. Okay, so in this first demonstration of projectile motion, we looked at the situation when a projectile is fired at a target in such a way that the projectile leaves the gun at the same time the target is dropped from rest, and the gun is initially aimed at the stationary target. The projectile will hit the falling target. We have two objects moving, target and projectile, and they are both performing two-dimensional motion, so we have to analyze them separately and show that the final positions are the same. So for the target, I've looked at the y component of the velocity because it's released from rest. It has zero velocity at the beginning, but it only has an acceleration on the y-axis, which is gravitational acceleration. And we used the velocity acceleration relationship to find the velocity at time t of the target, which is minus gt0 at the time of collision. And the change in the y position, the displacement, is the integral of vy of the target dt from 0 to t0, and we have the initial position yit minus 1 over 2 gt0 square as the final target position. And then from the geometry we can see that tangent theta initial will be equal to xt, the range of the projectile, yit, the initial position of the target, divided by xt. So you can see that the final position of the target is xt tangent theta initial minus 1 over 2 gt0 square. Then we analyzed the motion of the projectile. We looked at its x component of velocity, and it's going to be a constant because there is no acceleration on the x-axis, and that gave us an expression for t0, the time of collision. And then we looked at the y component, which is under an acceleration of minus g meters per second square, and we can determine the final position of the projectile at time t equals to t0 by looking at delta y, which is the integral of the velocity of the projectile dt in between 0 and time of collision. And we have seen that the final position of the projectile matches with the final position of the target, therefore they will hit. Okay, let's move on to another example of projectile motion. A projectile is fired up an incline angle phi with an initial speed v initial at an angle theta initial with respect to the horizontal. Theta initial is greater than phi as shown in the figure. Show that the projectile travels a distance d up the incline, where d is given by this expression, and for what value of theta I is d a maximum, and what is that maximum value. Okay, another projectile motion, we have to analyze x and y components separately. Now for the x component of the projectile motion, we have the range of the motion on the x-axis, xt, will be equal to d cosine phi, because d is the distance it travels before it hits the inclined plane. So we have the x component of the velocity is the initial x component, because there is no acceleration on the x-axis, which is vi times cosine theta initial. Ax is 0 meters per second squared. So what is the distance I travel on the x-axis? Delta x. Now assuming that I have these motion starting from the origin 0, 0, delta x is the range I travel xt minus 0, integral from 0 to t vx dt, which is the integral from 0 to t, the initial velocity vi cosine theta I dt, which will give me for the range vi cosine theta I times t. And xt was also equal to the distance I travel up the incline times cosine phi. Therefore, I see that what I'm calling t is xt divided by vi cosine theta I, which is d cosine phi divided by vi cosine theta I, which is the time of flight. Okay, so I have found the time of flight in terms of d phi theta initial and vi. Now let's take a look at the y component of this motion. On the y-axis, I have the final location yt is basically given by final position is d sine phi. You can see that from this right triangle here, xt, yt, d is the hypotenuse. So we have yt is equal to d sine phi. And the change in the velocity y component, delta vy, is integral from 0 to t ay dt, which is integral from 0 to t. Acceleration is in minus gj hat direction, so it's minus g dt. So we find that the velocity at time t minus the initial velocity is minus gt, and the velocity as a function of time is given by the initial y component, vi sine theta initial minus gt. And this must be equal to dy dt. Therefore, I can find delta y to be integral from 0 to t vy dt, which is integral from 0 to t vi sine theta initial minus gt dt. So I find that y at time t minus 0 so because it starts from origin, is vi sine theta initial. The integral gives me vi sine theta initial t minus 1 over 2 gt square. So the final position yt is vi sine theta initial t minus 1 over 2 gt square, which must be equal to d sine phi. So this yt is vi sine theta initial times t, which I have found to be d cosine phi over vi cosine theta initial. I can substitute that here. So it is d cosine phi divided by vi cosine theta initial minus 1 over 2 gt square. So I have to take the square of this time of flight. d square cosine square phi divided by vi square cosine square theta initial. This must be equal to d sine phi. Now you can see that this d will get rid of this d and this d. And I also have these vi's cancelling here. So I obtain sine theta initial cosine phi divided by cosine theta initial minus sine phi. So I take the right hand side to the left and take 1 over 2 g term to the right hand side. 1 over 2 g cosine square phi divided by vi square cosine square theta initial times d. So you can see that we have sine theta initial cosine phi minus cosine theta initial sine phi divided by cosine theta I is equal to, in parentheses, 1 over 2 g cosine square phi divided by vi square cosine square theta initial times d. And now this cosine theta initial will get rid of this cosine theta initial, and that takes me to my final answer for d, by noting that sine theta initial cosine phi minus cosine theta initial sine phi is sine theta initial minus phi. So my final answer for d is 2vi square. So this 2vi square goes to the top, and then I have a cosine theta initial sine theta initial minus phi divided by g cosine square phi. So there was a g cosine square phi here. It goes to the bottom. So this is the distance I travel up the incline, given in terms of initial velocity, the angles theta I and phi, and the gravitational acceleration g. Now, does that match with the suggested expression 2vi squared cosine theta I sine theta I minus phi divided by g cosine square phi? That is exactly what I have found. So this is correct. Now we want to maximize d by changing the angle theta initial. I want to travel the maximum distance up the incline. How can I do that? If I take the derivative with respect to theta initial of d, this must be equal to 0. So for simplicity, let's define a to be 2vi squared divided by g cosine square phi, so that I have basically separated d in terms of other stuff multiplied with the terms that depend on theta initial. Cosines, so it's going to be cosine theta initial multiplied by sine theta initial minus phi. So this is what I need to do. And I take the derivative of d with respect to theta initial. So first term, I will have sine turning into a cosine, a cosine theta initial minus phi cosine theta initial, and the derivative of cosine becomes a sine, so minus a sine minus a sine theta initial sine theta initial minus phi must be equal to 0. So if I open this up, I have cosine theta initial multiplied with cosine theta initial cosine phi plus sine theta initial sine phi must be equal to, because the a's cancel here, sine theta initial times sine theta initial cosine phi minus cosine theta initial sine phi. So you can see I will obtain a cosine square theta initial cosine phi here plus sine theta initial cosine theta initial sine phi. This must be equal to sine square theta initial cosine phi minus sine theta initial cosine theta initial sine phi. So in cosine phi parentheses, you can see that I will be obtaining cosine square minus sine square, which is cosine 2 theta. So this becomes cosine 2 theta I cosine phi. And on the other side, if I take this one to the right, sine theta initial cosine theta initial sine phi, I will obtain minus 2 sine theta initial cosine theta initial sine phi, which is minus sine 2 theta initial sine phi. So what I obtain here is cosine 2 theta initial cosine phi plus sine 2 theta initial sine phi, which is cosine of 2 theta initial minus phi equals to 0. So this means that this angle 2 theta I minus phi should be plus or minus 90 degrees. So that tells me that theta initial must be equal to plus or minus 45 degrees plus phi over 2. Now I note that I had this statement theta I must be greater than phi. So if I take the answer phi over 2 plus 45 greater than 5, this tells me that 45 is greater than phi over 2. This is okay. If I take the answer phi over 2 minus 45 is greater than phi, this will give me minus 45 is greater than phi over 2. This cannot be accepted. And I have phi less than 90 degrees clearly. So I have to take this answer. So this cannot be correct. I have to take this answer. So theta I must be equal to 45 degrees plus phi over 2. At this critical angle, I will have d maximum. Now, what is that maximum d? That was the second part of part B, I have to put this angle into the expression to find the maximum value of D. It is A times cosine theta initial, which is phi over 2 plus 45 degrees, sine of theta I minus phi. Theta I minus phi will give me 45 minus phi over 2. So if I open up cosine phi over 2 plus 45, this is cosine phi over 2 cosine 45 minus sine phi over 2 sine 45 degrees, which is 1 over square root 2 cosine phi over 2 minus sine phi over 2. Cosine 45 and sine 45 are the same, square root 2 over 2 or 1 over square root 2. If I look at sine of 45 degrees minus phi over 2, it is sine 45 cosine phi over 2 minus cosine 45 sine phi over 2, which is again 1 over square root 2 cosine phi over 2 minus sine phi over 2. Therefore, the maximum value of D will be A divided by 2, because I have 1 over square root 2 square, which is 1 over 2, cosine phi over 2 minus sine phi over 2 parentheses squared. So this will give me A over 2 cosine square phi over 2 plus sine square phi over 2 minus 2 sine phi over 2 cosine phi over 2. Cosine square plus sine square is 1, and 2 sine theta cosine theta is sine 2 theta. So I obtain a D max of A over 2 1 minus sine phi. So if I substitute for A 2vi square over g cosine square phi, this will be vi square divided by g cosine square phi 1 minus sine phi. So this would be my final answer for D max. Now you can also see that I can write this as vi square divided by g cosine square phi is 1 minus sine square phi. So it is 1 minus sine phi times 1 plus sine phi multiplied with 1 minus sine phi. These two will cancel, and I will find a D max of vi square divided by g 1 plus sine phi. Okay, so in this problem, we have a projectile up an incline. Inclination angle is phi, which is fixed, and our initial angle with respect to the horizontal is greater than phi. It's theta initial. And we have analyzed the x component of the motion with no acceleration. We have a constant velocity, x component, and with an acceleration of gravitational acceleration g, we have the y component changing in time. And we have found the time of flight from the analysis of the x component in terms of the d cosine phi divided by vi cosine theta I, and we analyzed the y component of the motion, noting that yt is d sine phi from the geometry. The velocity of the y component is changing with time, which is initial velocity vi sine theta I minus gt with constant acceleration motion on the y-axis, and we have reached the final y position by looking at the relationship delta y integral is equal to integral 0 to t vy dt, and setting that equal to d sine phi, we have determined d in terms of theta I, phi, bi, and g. And this expression matches the one suggested by the problem. Then the problem asked us what is the value of theta I that maximizes d and what is the maximum d. So for that, d as a function of theta I will be reaching an extremum value. Its derivative with respect to theta I must be equal to 0. Doing so, we have found theta I is 45 degrees plus phi over 2. And noting that theta I must be greater than phi, we have eliminated the other possible mathematically correct answer, making it unphysical. And substituting this value in our d expression, d as a function of theta I, we have determined the maximum value of